Yeah. Well, thank you for inviting me. My name is Sam Tai. I'm an applied research scientist working in Mobile Vision Group in Facebook. Our team focuses on efficient deep learning solutions for computer vision applications. So I'm doing this talk on efficient deep learning for computer vision on mobile devices. So today we'll talk about a few different topics. I'll show a few examples of AR on mobile devices. And then since we're actually running things on the mobile devices, we need to be able to make models that can actually run efficiently. And how do we do that? We try to make them efficient. Another way to do this is actually doing automatic search. And finally, I'll show open source version of Nametag to go, which is, if we have time, and talk about how we made it fast. So here is the body tracking work. So you can see the person is trying to move around, and butterflies are attached to this body. So what's happening is that on the phone itself is that we're running a person key point detection model, where the key point is like the joints of the body, the elbows, the wrists, the shoulders, the hips. With these, like a skeleton, you can then append different graphical effects onto the person, as you see. We're seeing a little bit on the phone right there. This is another. Oh, sound great.
Hey, Portal, call Laura. Wait, it's moving.
Like over here and follow it.
You can see up here, right?
Yeah.
Run past it like quick and back, rinse it in the sink. Now, you have a knife?
Oh, here, school developed in the Renaissance.
I 16. Then, now up. The mark of the world.
Sorry. Let me. Okay, so I don't think we need to go through the whole video. So the Portal is a sort of like a video communication device that we actually released last year. It has some smart intelligence built into it, as you've seen in the demos right there, where people are trying to run around, see the camera can still follow the person. So what's happening inside is actually there's also a person detection model, trying to figure out where the person is, finding out his body pose. And then with that, you can actually follow the person around. So you don't have to worry about standing always in front of the video conference device, and still be able to walk around and still talk to the person across the video connection seamlessly. This is another fun thing we did. This is called Instagram Nametags. Well, this is for Instagram. So I've used a lot of QR codes. I know that a lot of different communication chats or apps use this to connect with different people, and people can use that to, you don't need to type in other people's IDs. Instagram actually didn't have that feature for a long time, but however, when they looked at this problem, they wanted to be a little bit more open, because in Instagram, you can actually just search for usernames. So instead of using like a machine readable code only, we came up with approach just doing like a human readable code, while machine can also read it. So we came up with this for Instagram name tags. What's running behind is also a machine learning algorithm that does text detection and logo detection, and then using optical character recognition to recognize the text. So a lot of these actually are all run on the mobile device. So how do we actually make models that are efficient? There's a lot of things there's a lot of challenges. To be able to run on the device, you need to tackle several different things. Sometimes you'll need high accuracy. This is mostly because if you're doing AR effect, you want high accuracy because if it's not accurate, you'll see that there's actually jagginess, so it's not a really good experience. You definitely want faster speed for the reason that you want to run real time. But for mobile devices, typically the RAM is much smaller than compared to like GPU devices. So you want also the memory footprint to be small, where the memory footprint is the, when you actually run your device, running the inference, you want this the model weights, the activations to be small. Also, you want the packaged map model also to be small, where the package model may be transported over the network or actually is bundled into binary. So you all also want those to be small. So to just give a sense of like the accuracy, the complexity of different models that's developed over the years, shown here is a graph of all the pretty popular networks that's been released. On the top is the AlexNet, which was one of the first models that revolutionized deep learning. It was published in 2012 and became sort of like the ImageNet benchmark or reference that people would cite. This one actually had a very didn't have too much depth, and it was actually not too big of a model. VGG came out later, showing that if you just put in more weights, you can actually train a bit much better, gaining a much better accuracy. So you can see that actually improves the recognition accuracy. Later on, there's some works like the Google event, RISNet. Instead of using larger nets, they actually looked into trying to increase the depth of the network to try to improve the performance. Google event was the first one that actually was able to train more than a few tens of layers. ResNet, on the other hand, figured out a way to train based on residuals. With that, they can actually train like 32, 50, and I've seen there's been works on training with 100 and up to 152 layers. So these are like the larger models that typically can't run on mobile devices. On GPUs, it's also quite heavy as well. So people have started looking to using smaller models. StreetsNet was one of the earlier ones that actually was able to use only like 500 KB to run the inference. With that, it still achieves the same performance as the Alex model, but it's still not getting to the same accuracy as VGG, Google, and ResNet. MobileNet was the work that was done by Google. It was a pretty efficient model. You can see that it uses only a megaflop size of about only 500 megaflops, but it achieves a top-line accuracy that's similar to VGG. You have also different flavors of MobileNet, reducing it to almost a fourth of its size, with sacrificing some accuracy. ShuffleNet is another flavor of efficient model that was developed from another company. So these are different types of networks. You can see that there's a trend. These were actually proposed, I think, in just 2 years ago. These was much earlier. So there's a trend to actually try to make all these models efficient so that they can run on GPUs faster or even like mobile devices. But how do we actually make these models efficient? Well, one simple way to actually reduce these, to make these models more efficient is by pruning. In these networks, there's actually a lot of weights that may not need may not be that important. So if you can actually figure out like the different weights, different information, to figure out the ones that's important, we can then try to prune these out. You typically can use these pruning approach to prune the weights by sometimes up to 9 times, between 3 and 9 times based on the model performance. You can also then do quantization, where you quantize the representation of the weights. To just give an example, shown here is a kernel size, say a convolutional kernel of 4x4. Typically, we only have a convolutional of odd, so this is just for illustration. Once we have these kernels, we can do k-means clustering to cluster them into different indices. The colors show the indices, and the numbers here show the index. So you can actually just represent the whole original weights by using the cluster centers and the centroids. However, if you just use these directly, you'll find that because you did some quantization, your accuracy actually drops quite a bit. So you need to do some sort of fine-tuning. And the way you do fine-tuning is that you also run the same network, you figure out the gradient update rates, and then because you know the assignments of these different indices, you can associate them together, and then you do an average-based weighting to update the weights again. Typically, when you use this approach, you can regain the losses that's due to quantization. Shown here is a graph of if you use pruning and quantization to quantize a model. This is a model that's already pretty efficient. This is a small model with a model size of just around 1.8 megabytes. This one has an accuracy of 40 or 50 something. So if you do pruning and prune from the original size to the sparse side, you can actually get it around by pruning away 63% of the parameters. And if you represent the centroids by using just 8 bits, you can reduce it to probably just 300 bytes. From the original size to 8 bits, it's reduced by almost 8 times. If you notice here, you can actually almost get away with also 5 bits as well, if you can allow your application to do that. So pruning and quantization is an efficient way to actually reduce the model size. As a byproduct of pruning, though, you can actually also improve the accuracy. Once you do the first training using the dense network, you do pruning to reduce it to a sparse network. Then, when you train on this, you force the network to learn specific items. But sometimes there are still losses in particular information. So another way to improve on those is just repopulate the network again, and then you train again. This actually is an efficient way to actually improve performance as well. On Google NAS, we found that this actually improves the performance by, this is split. So originally we were showing the accuracy, this one's actually showing the error. So with the Google NAS, using the Dense-Sparse-Dense approach, you can reduce the error by almost 1.1 times. BGG actually got a great boost. It decreased the error by 4 times, beating Google NAS. ResNet and ResNet 18, ResNet 50, each got about 1.2% error reduction. So these are not small, trivial improvements. So using this approach, you can improve the training accuracy. So we talked a little about quantization of the weights, improving the training, but another side of the problem is actually activation. So when you do the inference, the input image size is actually pretty large. For a given image, it might be something like 224 by 224, and then you pass it in through the network, the channel size gets larger. So it actually is a large. It's a large portion of the memory use. So how do you actually quantize the activations? If you look here, what we've shown here is the activation and weight distributions of the model. Weights you can quantize using the quantization approaches we mentioned. The activations, and you can also do linear quantization. But if you just do linear quantization, and you train the network, sometimes the performance is not that well. So what we found is that you can use a value-aware quantization to actually improve the performance. So what does that mean? Instead of quantizing the activations directly, you only quantize the activations up to a certain level. So with these activations are represented using 3 bits, for example. And the rest you represent as full scale, full floating points, full 32 bits floating point representation. Because the higher the weights, typically there's more information. So with that, you can actually be able to retain more information where you're actually doing the training. Using this approach, you can actually reduce the activation weights quite a bit. You can even do on-device training with this approach. For example, SqueezeNet, the original model size was only just a few hundred K bytes, but the activations is actually 1.5 gigabytes. If you use activation quantization, you can reduce that to just 640 megabytes. MobileNet, similar situation. The activation set memory use is around 7.3. If you reduce it with activation quantization, you can reduce it to 1.1. ResNet also from 9 gigabytes to 1.52. You notice that the line on the top is actually the ImageNet accuracy. You see that there's almost no drop in when you're actually doing this quantization. All right, that's a quick introduction of like different techniques. Now we'll dive into a little bit more, talking a little bit more about architecture search. So all the previous method I've mentioned is actually just modifying the model as it is, quantizing the weights, quantizing the architectures. This is only one part of the work. If we can actually get more efficient models, then this is actually an even better approach. Getting efficient models previously has been done mostly through human understanding. So in a ways, we spend more time looking at it and see how it gets improved. So moving from AlexNet to BGGNet using higher parameters, BGG to GoogleNet with deeper networks, from GoogleNet to ResNet, even deeper networks. There's a lot more work actually also like combining different layers from different parts of the network to go deeper. But all these would require a long time. So automatic neural object search deals with the problem actually, instead of doing human-based search, you use computers to help you find better networks. So you use machine learning to search for machine learning architectures. Well, on this end, we have done two works to work towards this goal. One is a model adaptation framework. So what is a model adaptation framework? So for different mobile devices, typically the hardware would actually be different. Each different type of hardware can have different performances. So convolutional kernels or decisions or libraries, these would actually all result in different latency. Sometimes, if a smaller kernel size versus a large kernel size, if the memory footprint is the same, it can actually run at the same speed. So sometimes it might be good to actually choose a 5x5 kernel over 3x3, which you might actually get a better performance. So how do we do that? Well, if you just look at the whole network, sometimes there's a whole bunch of layers, and you have all these parameters inside. The number of search space you have to look into is quite large. Just give an example, like if you search for a kernel size 3x3, 5x5, or even 7x7, that's 3. You might have to consider sometimes, like if you use a mobile net model, there's expansion ratio. So if there's expansion ratio that could have probably six other choices. You also have like a number of channels within each layer that can actually have more than 10s. So you have like 20 different options that you can choose from inside each layer, and you have 10 layers. That would be 20 to the 10 times. So the search space is pretty large. You need to search through that search space to find efficient models. If you do this just through a brute force approach, that won't actually work. To do this efficiently, what we did is that we built a method to actually try to do an efficient evolutional search. We try to estimate the accuracy. This can be done by using the base network and doing a random sampling of the search space, and using Gaussian process evasion optimization to try to estimate the accuracy. Once that, you can actually get a sense of which direction you need to go. On the latency side, since most operations are dependent on hardware, we can simply just pre-test them using different kernels, different sizes, different channels, using that to build an operation latency lookup table. Once you have these operation latency lookup table, then you can have a prediction, a latency predictor. similar fashion, you can use that to also predict for energy as well. So with accuracy prediction, latency prediction, and energy prediction, we can then create efficient models that's accuracy, latency, and energy aware. The name we call this adaptation framework is called CamNet, which comes from chameleon net. Yeah. So this is a short result of our adaptation results. There's a lot on the curve, so I'll go through them from top to bottom. On the top is MobileNet V2. You can see that on behind it shows that it's 224, which means the input resolution. Typically, if you want to speed up your network, there's two options. One is to change the input size to a smaller size. The other is to try to scale the channels that's used within the network. So the curve you see with the MobileNet V2, which is the blue one, this curve is traced by changing the channel size, downscaling them. But you can see that if you just change the resolution to say 192, you get a performance when compared to actually scaling the channel size. So people try to find different ways to try to find better performance and trying to curve out like a better curve on top. MobileNet has these performances. NASNet, which is also a network architecture search method, has a performance actually shown here, also pretty good. ShuffleNet is another flavor of efficient model that has a performance right here, and CamNet is ours. So because we are hardware aware and latency aware, we are able to find out the ones that works best for Samsung S8. And then we can actually get a performance that outperforms all the others. If we look at just the last point where you have focus on just 4 milliseconds, we have much higher accuracy. CPU is one situation for the hardware. We can also run it on the DSP device. If you use DSP, typically you have a better kernel to run the convolution, so you get a little bit better performance compared to the CPU. You can see that, for example, under the same latency constraints at 30 milliseconds, it gains about 1.3% accuracy improvement. At the lower end of 60, at 4 milliseconds, it gets almost a 4% improvement. So I talked about, so all these methods are actually still based on looking at adjusting the parameters of a given architecture. But you can actually also do architecture search directly. So when you talk about architecture search, you'd be looking at something like MobileNet is using inverted residuals to help with their network. ShuffleNet is using a group convolution and doing shuffle across different layers. All these can be actually put as a single element within the search space that you can actually search for. Traditionally, well, not traditionally, in the past few years, a lot of people have looked into this problem. One particular approach is actually doing a genetic programming-based approach, where you form different architectures, try to run those networks to figure out the top 10 best performing models. You mutate it slightly, or you join them together, and try to run it again to see if you actually better models. So typically, this approach is pretty random, and it takes a lot of GPU time to actually find out better models. In differential network architecture search, instead of doing genetic programming, we propose a way to actually search the space directly using the differential network architecture search. What this means is that we can actually create a stochastic supernet where each layer contains all these different sorry, it's not working. So each layer actually contains all the different blocks within your search space. And we use a method called double softmax so that it can actually it can actually figure out which building block to use. And when you train the network, it can decide which building blocks to use. For example, the distribution here, it points out to what actual architecture is used within each layer. So with this, you can build out different type of layers. To just give an idea, on the top are 6 different configurations or basic architectures that we use to search for. We search for different methods. On the top 4, top 6 are architectures that we search for. You can actually make it also hardware dependent. Like this one particular here, this is a search specifically for Samsung S8, or you can actually search architecture specifically for iPhone X. We create our search space so that it actually can contain different type of networks. For example, MobileNet 2 has the architecture that's shown below, whereas NSys has this other particular network. Using this approach, we get a performance that's shown here. It's much better than MobileNet V2, and then also better than ShuffleNet V2, and a little better than MNASnet as well. And if you remember, the MNASnet actually has a performance that's almost similar to the model adaptation framework. So this actually, because you're actually doing the architecture search, you have a little more space in finding better architectures. And one thing I mentioned is that you can target devices. You can find the best architecture for different devices. Shown here is the performance for iPhone X and Samsung 8. The blue bar is when you search for a model that's specifically for the iPhone X. It performs better on the iPhone X, but not on the Samsung S8. And if you train on the you search for the model for the Samsung S8, it works better on the S8 and not the iPhone X. So to recap a little bit, to do model adaptation, there's different goals that you would look into. If you want a smaller size, a simple approach is to do pruning. You could do pruning. You could typically remove 60 to 70% of the redundant weights. If you use weight sharing, you do King's cross-chain as weights. Use this representation. You can actually reduce the representation even further. You can even do more quantization to reduce it to even fewer bits. To get higher accuracy, you can use Dense-Sparse-Dense to try to figure out how you can actually get better accuracy. Another thing I haven't talked about distillation today is that you can actually use a larger network to train a smaller network. This is a technique we call distillation. This would help on increasing the accuracy of smaller models. And finally, for faster speed, we talked a little bit about a latency-aware model design, which is adapting the model to target a device to improve speed. You can go to automatic architecture search to find better efficient models for different devices. You can also try, the below 2 are things that we haven't talked about today. You can try parallelizing all the network, getting bigger networks to try to see if you can actually run things more in parallel to get faster speed. And finally, you can also go with low precision networks, where this low precision means the precision of the weights and not the final results. But typically, low precision networks require some level of hardware support. Nowadays, I think networks with like 3 bits can actually perform pretty well, pretty comparable to actually full precision networks. Yeah, thanks. Yeah, thanks. So I think this is all the things I want to talk about making models efficient. Lastly, I'll just show a quick demo of real-time post-estimation. The thing that you saw with butterflies is the final effect. This is a demo of the actual case. Oops, sorry. what you saw here was actually a master RCN to go running on the device. This was running, this demo we did in 2017 actually. So this is running on a Samsung S9 or NES, I think it's sorry, Galaxy S7 actually. This was running at 20 frames per second. The information we get from the image is the bounding box of the person and the key points, which is the joints. These are actually running frame by frame, so we're not actually using any time information. So the speed is actually pretty fast. The network itself is master CNN network that looks like this. It's a detection network where you transform the input image into a smaller feature map, and then you have a region proposal network to figure out interesting points within the image, and then you do a cropping and resizing to a smaller map, and then use that to infer a class and the refined bounding box. Once you have those, then you can then get a larger map and do mask generation or like key point generation, which finds like the different key points. Shown here is another graph that actually points this out. You have the key point head that does finding the key points, and the segmentation head. The original network is actually pretty huge. It actually doesn't perform as fast. What we did to actually speed it up is to, well, as we mentioned, reduce the number of layers inside the network, reduce the channel size, try to compress the model, try to prune the model. Another thing that helps with actually making this fast and runnable on a single device is that you use a smaller detection head. One of the things about detection networks is that for each different interesting parts in the image, it runs a detection head. So if you find too much things, this becomes too heavy to run on the device. So you want to use a small detection head, and you limit yourself to only a subset of the interesting points of the image. But of course, if you want high accuracy, you still want to have high input resolution. With that, I thank you for your attention, and that's pretty much what I wanted to talk about today. And we're also hiring as well, so if you're interested, you can use this email below.